Welcome to ECE 476 Advanced Embedded Systems, lecture number 27. In this lecture, we're looking at I2C Communications. Now, specifically, what we're going to look at is how to measure the height of a building using a BME 280 pressure sensor, or using a GY521 accelerometer to measure how high you can jump. For example, here, I'm going up the stairs of Ag Hill building, measuring the pressure drop using a pressure sensor interfacing with an I2C interface. Or here I have a GY521 accelerometer connecting through an I2C interface. I can measure acceleration versus time. So when I sit there and drop it, I can see the XYZ acceleration all recorded through I2C interface. So that's kind of where we're heading. How do you get I2C communication to work on a Raspberry Pi Pico? So starting out, I2C communication is one form of serial communication. Previously we looked at SPI. With SPI, you need 4 wires. There's chip select, clock, transmit, receive, sometimes called master in, master slave out, master out, slave in. I2C, in contrast, uses 2 wires. One is the data line, a bidirectional data bus, and clock. Clock comes from the master. Now with the Raspberry Pi Pico, there are a couple I2C functions. They're in the machine library. You have capital I2C. This one declares an object that's an I2C interface. There's scan. This looks for I2C sensors attached to a bus. I've got write to and read from. I can write to the sensor, read from the sensor. Set a start condition, set a stop condition, or do a read or write from memory. So we're going to be using those to read and write to an I2C device, specifically a BME temperature, pressure, humidity sensor, or a GY521 accelerometer. Now with I2C, the data is communicated in packets. When you start a message on an I2C bus, that's indicated with the data line switching from high to low before the clock line switches. That is followed by the address. Who am I talking to? You can have multiple I2C devices on the same bus. Whether I'm reading or writing to it, acknowledge. Then the data, followed by a stop condition. That's what the data looks like. The style of communicating with I2C is a little bit different. With SPI is kind of more like a computer language. I am sending commands to the slave, to the sensor. I want you to do a reading. I want to get this data. Here's what I want you to do for setup. That's SPI communication. I2C is a little bit different. With I2C, instead you're reading and writing to registers. So I've got a sensor over here. It's controlled by some registers that tells you the sampling rate, the bandwidth, stuff like that. When I collect data, it writes to register. The Pico can read from the read registers. It can write to the write registers, and through these registers, it communicates with the sensor. So the style is a little bit different. In terms of the Pi Pico, there are 2 I2C buses. They can be connected to multiple pins, your pick. But again, you can have 2 different buses running at the same time. On any given I2C bus, you can talk to multiple devices, as long as they each have a different address. So probably the best way to explain this is to give an example. Let's look at a sensor we've looked at before, a BME 280, that is a temperature, pressure, humidity sensor. You can communicate using SPI or I2C. Let's look at I2C. With I2C, you've got to give the sensor power and ground, kind of given. Plus, I'm going to transmit and receive data using just 2 wires. I'm going to use actually an internal pull-up resistor, so I don't need an external one. The Pico has that feature. Now to start out, if a device is attached to the I2C bus, I need to know what the address is. Well, there's the I2C command scan. What that'll do is that'll tell you everybody that's connected to this I2C bus. So to start out, I'm going to import machine. From machine, use the module I2C. I'm going to connect to I2C bus 0. My clock line will be pin 1, the data line pin 0. And again, it's kind of arbitrary. Goes back to, these are the options you have for I2C bus 0. I'm just going to choose 0 and 1. I will then scan all devices attached to bus 0, and it will save them into devices, and then print the results. So in this case, if I attach a BME 280 sensor to it, it comes back that, yes, there is somebody attached to the bus. It is device number 76. That's the ID of the device. This number, I need to remember that. I'll need that for later. When I read and write to the bus, two fairly useful routines are register read and register write. What these do is I'm going to pass data. This is the device I'm talking to, which is device hex 76, my BME 280 sensor. This is actually I2C. That's this guy right here. I'm going to do an I2C write. Here's the address. That's hex 76, the sensor I'm talking to, which register I want to write to, and the data I want to write. There's also register read. Same thing. I want to read a register. How many bytes do I want to read? So these two routines I'll be using over and over in the following lecture. Before I read and write to the device, I kind of need to know what registers are important and what the different registers mean. This is where you go to the data sheets, look up a BME 280 register map, and this is what you'll find. Address F5 is a write register, that's configuration. F4 is control measurement. F2, control humidity. The read registers, status is at F3, humidity reading, temperature reading, pressure reading. And there's a couple more. We'll just kind of stick with those for now. If you look through the data sheets, it'll spell out what the different registers mean. For example, when I write to F5, I'm writing 8 bits. The top 3 bits control the standby. When I take a reading, this is how long it pauses between readings, kind of sets the sampling rate. These 3 bits set the filter. It does a first order low pass filter, and A is where the pole is. If I have zeros right here, there is no filter, and the bigger A is, the slower the RC time constant. The last 2 bits tell it whether I want to communicate using I2C or SPI. We'll be using I2C. If I look at the data sheets for register F4, that's control measurement. These 3 bits control the oversampling. Basically take, let's get 16 measurements, take the average. 2 measurements, take the average. Kind of one way to reduce the noise. Oversampling on the pressure measurement and the mode. Sleep, forced read, or 1-1 normal read. We'll be using 1-1. F2 is for the humidity measurement. Sets the oversampling, basically how many measurements do you take the average, return the average. And finally status. While bit number 3 is 0, it's doing an A to D conversion. When it goes to 1, the conversion is complete, and I'm ready to read the result. Okay, so with all that, one more. And you have to know where the data is located. Again, from the data sheets, the humidity is a 16-bit number located at these 2 memory locations, those 2 registers. Temperature is a 20-bit number located in these 3 bytes and those 3 bytes. Temperature and pressure are left justified, so the right 4 bits are all zeros. Okay, so with that, let's do a couple examples. Let's set up, using I2C Communication, set up the BME 280 sensor for 500 millisecond sampling rate, no filter, I2C communication. The bit pattern that I want will be hex 60, so that goes to config, memory address F5. To set to 16 times oversampling, normal operation, I'll set control measurement to FF. The commands to do that would be a register write. I'm going to write to the I2C bus. This is 76, the address of the BME 280 sensor. I'm going to write to F5, and here's my data, 60. Write to register F4, data is FF. Once I've done that, I can now start reading the sensor. If I want to read this the raw reading, I can just read the data at address FA, FA plus 1, FA plus 2, reading 1 byte at a time. Convert that to a 20-bit integer. So left justify 16, shift that one left 8 times, plus x2 gives me a 24-bit number. Shift it right 4 times, gives me a 20-bit number, 0 to something big. That's my raw reading. So let's see that in action. Here, this is the scan program. I just want to see who's on the bus. I've got device number 76. That's the BME 280 sensor on I2C bus 0. Next, let's look at the raw A to D reading. So here I'm doing a raw reading the temperature sensor, just returning the 20-bit number that comes through. Okay, so as I run it, if I heat it up, you can see the number is getting bigger. That's the raw temperature reading. To convert to degrees Celsius, this is actually kind of a convoluted process. If you look through the data sheet, this is the conversion from the raw reading to temperature. It's a parabolic curve fit. The constants, T1, T2, there's T3, there's T3, those are stored in other registers on the BME 280 sensor. Once I get those constants, I can then convert the raw number to degrees Celsius, and here's your reading. In terms of where those constants come from, T1 is from address 88, 8A, 8C. Control your constants T1, T2, T3. Here's the equations for them, if you care. I can then take the raw reading, convert to degrees Celsius, and print them. So like these are the three constants, T1, T2, T3. Those will differ for every BME 280 chip. Those are factory calibration numbers. This is the raw temperature reading. Converting to degrees Celsius, this is the temperature. My room actually is kind of toasty. I have a temperature reading. And kind of note the I2C interface is really easy to use. Once you get this algorithm set up, all I'm doing is I'm just reading some register locations. Once I have that, do some calibration functions, there's my reading. A little bit different style than SPI. If you plot the temperature versus time, this is done with a conversion time of 1,000 milliseconds using 16 times oversampling, second order filter. Here's the temperature versus time. Temperature is increasing. That's just sun's coming in the window in my office over, whatever line that was, about an hour. Temperature raised about 1 degree Celsius. That's what the raw temperature reading looks like. Fairly clean data. That's for reading temperature. If I read a different location of memory, address F7, F8, F9, I have the pressure reading. So the procedure is really about the same. I'm going to read a different location. That's going to give me pressure. Read different constants. Those will do the calibration. Again, rather convoluted algorithm. That's what's given in the data sheets. And note that the algorithm for converting the raw reading to pressure includes temperature. So I need to know what the temperature was. Go through all this. I've got a pressure measurement. So once you go through all that, the reading temperature and pressure is actually really easy. I'm just going to do read temperature. That gives me temperature in degrees Celsius. Read pressure. It needs to know what the temperature is for the calibration function. Returns pressure in H pascals, and print them. So if I run that, also prints the LCD display. I'm attached to a device at 76. That's the BME 280 sensor. Here's the time in seconds. Here's the temperature in Celsius. There's the pressure in H pascals. If I put my hand around the sensor to warm it up some, you see the temperature is going up. I'm not really sure what to do to increase the pressure, but if you did, that would go up too. If I let this run for about an hour, I can show what the pressure does. So here's the pressure going up and down. Again, not too surprising, that's actually real data. On windy days, wind is caused by changes in air pressure. The BME 280 sensor can pick that up. So that's what's happening the day that I measured it. I'm getting a resolution better than 0.1 H-pascals. So here's a question for you. If I can measure pressure that accurately, can I measure the height of a building by measuring the change in air pressure? What I want to do is go to the A.G. Hill building on NDSU campus, go from the basement to the third floor, and see, does the air pressure change enough that I can measure it? Well, I can measure pressure to 0.1 H-pascal pretty easily with the BME 280 sensor. If you go to a website that does a air pressure versus height calculation, I should have a change of air pressure of about 2 or 3 H-pascals, so I should be able to measure this. This is the A.G. Hill building on NDSU campus. I'm going to try to measure the height of the building using a BME 280 pressure sensor. I am currently in the basement of the A.G. Hill building on NDSU campus, and using a BME 280 sensor, I'm measuring the air pressure. What I'm going to look at is when I go up the stairs to the third floor, does the pressure drop, and can I measure that? Here I am on the third floor of the A.G. Hill building on NDSU campus. As I go up, the air pressure should drop, and I can see the BME 280 sensor has detected that. Air pressure has dropped by 3.73 H-pascals as I went from the basement to the third floor. As I go back to the basement, the air pressure should increase. Here I am, back in the basement at the A.G. Hill building on NDSU campus. As I went down the stairs, the air pressure increased, went from -3 H-pascals to -0.4. So the air pressure increased by about 3.6 H-pascals as you go from the third floor down to the basement. You can definitely measure the change in air pressure as you go up and down stairs using a BME 280 pressure sensor. So let's try it. Starting out in the basement, I ran up the stairs, took the air pressure measurement, ran down the stairs, took the air pressure measurement. Here's what it looks like. So for 100 seconds, I'm in the basement. Air pressure is fairly constant. Ran up the stairs, air pressure drops. As you go up, air pressure drops. Hold out at the third floor. It looks like there's some filtering going on. Stay there for 100 seconds. Run back down the stairs to the basement. There's your air pressure. So the change in air pressure was about 3.5 H-pascals. Pretty clean data. I can definitely measure that. If I go to omnicalculator.com, there's a way to calculate or equate height versus air pressure. If my height changes by 15 meters, the air pressure should change by about 1.9 H-pascals, or a sensitivity of 7.89 meters per H-pascal. The air pressure changed by 3.5 H-pascals. Therefore, I conclude the height of the Ag Hill building is 27.6 meters from the basement to the third floor. That kind of seems kind of high to me, but that's what the data says. So apparently I can measure height of a building using air pressure, at least using a BME 280 sensor with an I2C data interface. Let's do another example. Let's use a GY521 accelerometer connected to a Pi Pico. So again, we looked at that, one of the sensors we looked at. Here we're just going to look at it straight from the I2C bus standpoint. The first thing you need to do is connect the sensor to the Pi Pico using an I2C interface. I'm going to use transmit and receive as so. Second thing I need to know what registers I need to read and write from. Going to the datasheet, address 1A sets the sync, set, and DPL configure. A sync set allows you to synchronize the sampling rate based upon temperature, gyro, acceleration, Set to 0 if not using. I'm not using it. DLP is the digital low-pass filter configuration. I can set the bandwidth of the filter from 5 Hz to 260 Hz. The acceleration configuration enables the self-test on the accelerometer, and SEL sets the range. Do I want to measure acceleration up to 2 Gs, 4 Gs, 8 Gs, or 16 Gs? I'm going to be using 2 Gs. And then the power management lets you turn on and off the sleep cycle, clock select, using 0, normal operation, normal operation, normal operation. And then once set up, I can read the acceleration. That's located at these memory addresses. 3B, 3C is X, 3D, 3E is Y, 3F, 40 is Z. Okay, so with all that, I can set up the GY521 accelerometer to have 260 Hz bandwidth, plus minus 2G range, 8 MHz internal oscillator, as so. I'm going to first find the device, set the bandwidth, set the range to plus minus 2 Gs, set the clock frequency to 8 MHz. The acceleration can then be read with this routine. I'm going to pass, where do I want to read? So this is X, that's Y, that's Z. Read 2 bytes at that address, convert to a 16-bit number, scaled by your range, plus minus 2G. And here's what she looks like. So here's the code. Range is I set it up to 2, plus minus 2 Gs. That comes from this configuration register. I'll read the XYZ acceleration, convert to a string, so it's prettier to see, print it, wait 0.1 millisecond. So here's my reading. And what you're seeing is, if we rerun this, it looks for what's attached to my I2C bus. It's device number 68. That's the GY521 accelerometer. Here's the acceleration in the X direction, Y and Z. If I hold it flat, it's pointing straight down. Flip it over, it's now plus 1 G. Sideways, this is Y is now pointing down. Rotate 90 degrees, X is pointing down. So there's my XYZ acceleration. All found by reading registers. That's kind of how the I2C bus works. You read and write to registers. Okay, so let's have some fun. Let's see if I can measure how high something is by dropping it. So like one way to measure the height of a building using a barometer is to drop it. See how long it's in free fall, or actually in this case, an accelerometer. See how long it's in free fall. So what I have is a program. This is the GY521 jump program. The program will wait until I hit a button. Once you hit it, it collects 2 seconds to data and then plots it on the screen. So let's kind of show what that looks like. So here, I'm going to start the acceleration, drop it. That's your acceleration versus time, XYZ. Doing it again. Okay, so with that, I can start having some fun. Suppose I drop the sensor from 50 centimeters. Can I measure how high I dropped it by measuring how long it's in free fall? So in free fall, it should be experiencing 0 Gs right here. And this is what the data looks like. Not exactly 0, but if you kind of say whenever the net acceleration is less than 0.5, call that free fall. I can measure the time of free fall as being 0.32 seconds, or 50.1 centimeters. Yeah, about what I expect. Now that works. Suppose I were to hold this in my hand and jump. So I'm going to sit there. Here this is. Hold it in my hand, push the button, jump as high as I can, land, measure the acceleration versus time. This is what she looks like. So this is with a 10 Hz bandwidth with a 260 Hz bandwidth. You can see the 10 Hz is a lot cleaner, some delay. 260 is much more responsive, a lot more noisy. That's when I hit the ground. Can I measure how high I can jump? Well, again, let's take the time where my acceleration is less than 0.5. Call that when I'm in free fall. That's about 0.33 seconds or 0.40 seconds. From this, I can calculate how high I can jump. Distance is 1/2 AT squared. When I jump, this equation is from the apogee to ground. My total time is double that. So take the total time divided by 2. So half of it is going up, half going down. Gives you this equation, 1/8 AT squared. I know t, that's right here. I know acceleration due to gravity, 9.8 meters per second. Calculating, my vertical leap is right around 13 centimeters, which is not real impressive. It used to be higher. I used to play volleyball, but that was like 20 years ago. Hey, I'm getting old. Anyway, that's about right. So I can do things like measure acceleration, measure how high I can jump, measure how tall a building is with the accelerometer, let's do that again. Watch what happens when I rotate it around. So rotate the sensor around. You can see the XYZ acceleration changing. This is going from +2 to -2 Gs. That's the setup I have right now. All stuff you can do. So kind of in summary, I2C communication is actually pretty darn easy with a Raspberry Pi Pico. With it, you're reading and writing to registers. You're writing to registers to set the bandwidth, set the sampling rate, etc. You're reading registers. That allows you to read the sensor's data, get calibration constants, and so on. With the data sheets, you really need the data sheets in this case. Data sheets are really helpful. They tell you the address of the registers, they tell you what the registers do, and they tell you what the data means. But given that, I2C communication is one way to read sensors that's pretty straightforward. Different style than SPI, but just another way. That is lecture number 27 for ECE 476.